Hello, this is NCC-171D Free Vulcan, and earlier this week on Wednesday was the 100th anniversary of Albert Einstein's General Relativity being published. In addition, on Wednesday, the LISA probe was launched, which is a mission led by the European Space Agency in collaboration with NASA. So I'm going to talk about those two things because they're actually very related. So, general relativity, or the history of general relativity and it being the 100th anniversary of its publication, is that 100 years ago, last week on Wednesday, Albert Einstein first sort of talked about the theory of general relativity, not to be confused with special relativity, which he'd come up with, I think, 20 years earlier, in 1905. And he gave a talk about it at the Royal Prussian Academy of Sciences on November 25th. And then a week later, on December 2nd, 100 years ago from the Wednesday of the week I'm making this video in, the theory was actually published. Now, the theory of general relativity is based on the equivalence principle. And the equivalence principle is, I've drawn some little rockets here to help explain, the idea that, so ignore this one, this one, and this one for now, but it's the idea that if you pretend you're in a rocket, and the rocket has no windows, and all of a sudden you start feeling, or you start accelerating downwards to the floor of the rocket for some reason, you can't tell the difference between whether the reason you're falling or accelerating to the ground bottom of the rocket is due to the rocket being in constant acceleration in the opposite direction, like in this picture, because if it were in constant acceleration, then from your perspective, it would appear that you are falling at a constant acceleration to the floor of the rocket or to the other side of the rocket. Or it could be that the rocket is on a planet which has a constant acceleration, and that's why you're falling to the floor of the rocket, because of the gravitational field of the planet. And the whole idea is that you can't really distinguish constant acceleration from gravitational pull. So, you have these two ideas, and then the next thing you do is you sort of have a thought experiment of, say you're in a rocket in constant acceleration, and someone shines, like, a flashlight or, like, a laser beam, and they shine it, say, at this point. If you're looking down, like, as you're beginning to fall, or if you weren't falling, I guess, you would see that, or from your perspective, say he's, like, hanging on to the side, or even if you were falling, the light, or, like, the laser beam, or the flashlight, or whatever, would start, say, at this point, but then because you were accelerating upwards, and the light would not be accelerating upwards, it would continue what was a straight line, and you would see the light hitting at a lower point because of your acceleration upwards. This is obviously exaggerated. And because of this, and the special theory of relativity saying that light is always constant, if you're accelerating and it's moving downward, then that would affect light, so then time has to be affected. And because of the equivalence principle, if it works in this scenario, that means that the gravitational acceleration must also bend light. So then, the ideas that sort of come out of this were basically general relativity, and the main one is sort of that mass distorts space-time, and it's the distortion that mass causes in space-time which causes gravity. And one way that you can think of that is sort of in the picture up here, that if you think of Earth on, like, a fabric, then if you put it, sort of drop it, then it'll distort the fabric around it. And, of course, this is, like, two-dimensional, but then those distortions are what cause objects to be attracted to it, and why objects with mass attract each other because they distort space-time. And some predictions that come out of this are that gravity bends light, so sort of this thing, that gravity affects time, black holes, because it's a bit more complicated, but basically, because gravity bends light, in an orbit, there's a certain escape velocity, and if these to get out of the orbit, and if the escape velocity is the speed of light, then that means no light will come out of the black hole, and because nothing can travel faster than the speed of light, nothing can come out because light's trapped, so any light in the black hole, or that's at the escape velocity, will then travel around the black hole, and all light inside and all other objects, because they can't exceed the speed of light, can't get outside of the black hole. And the event horizon, which is sort of what we think of the edge of the black hole, is the point where the speed of is like the radius of where basically if light's coming in, where light will start bending around and being trapped in the gravitational pull of the black hole. And then it predicts gravity waves, which are sort of like as mass distorts space-time, sort of like the wake of that, like the effect of it, because here, I'll get into this in the next slide, because the next slide is just about gravitational waves. And the idea about gravitational waves, as I was starting to describe, is that as mass distorts space-time, and it's moving through space-time, the distortions take time to sort of travel through space. So, like, for instance, one famous example, I think, is like if you suddenly took away the sun from our solar system, it would take time for the Earth to stop orbiting the sun, because gravitational waves can only move at the speed of light, so it would take time for the distortions to change and catch up with Earth. So until, I think it's 8 minutes or something, that light coming from the sun reaches the Earth, until that same time elapses for the gravitational distortions to reach Earth, Earth will continue to orbit the sun because the gravitational distortions that are reaching are still there, and it'll take 8 minutes for the distortions to catch up. And that's sort of what gravitational waves are, that if you, say, have like two objects orbiting each other, they'll create distortions that then travel out away from them. And yeah, so I said they travel at exactly the speed of light, and the reason they can do that is because they're waves, not mass. And the reason they don't do it faster, I think, has something to do with the math. I'm not exactly sure. It just sort of, the way in which the distortions work in space-time works is like that. But the reason that they can be that fast at all is because it's not like a mass moving, it's just the fabric. It's like the effect sort of the fabric and the fabric of space-time changing. So the next thing I'm talking about is the LISA probe, because the whole point of the LISA probe, which was launched, I believe, on the same day, in fact I'm almost certain it was, because that's when I saw the news article about this, is being launched for the purpose of, from what I understand from reading the articles about this, to test the technology that might be used in order to detect gravitational waves. Because one thing I didn't mention, if I go back up here, is that all of these things, more or less, we've had tests for to test the effect. Like, we can test and verify, we've done tests that verify that gravity bends light, and that gravity affects time, and black holes another effect, but it's not, I think we've observed black holes indirectly, but we haven't actually really verified gravity waves and tested that they exist. So this is the one consequence of general relativity that hasn't been fully tested yet. And the LISA probe is testing Sorry, the recording got off. But the LISA probe is testing technology that could theoretically, detect gravitational waves by measuring really small differences in length, and these probes would be launched in orbit, and then they'd measure the distances between, there'd be a bunch of little satellites that would be in alignment, I presume like this, because this was a photo I found of it, and they would measure the distance between each other to extremely high accuracies. On the article I read, it said less than the length of an atom, and I think the idea is that if they were able to do this, then when a gravitational wave passes, because it's a distortion in space-time, it would distort the space between the satellites, so then it would change the distance they measured, and that's how we would know that a gravity wave had passed. So in this way, they would be able to detect gravity waves. And that is about it. Ooh, dear. So, these are the articles that, or some of the articles, not quite all of them, that I used to make this, and I will, or that I read up about this in, and I will put them in the description. This is NCC 171D for Dave Vulcan saying live long and prosper.